Okay, let us start. So last time we discussed how to calculate such a correlation function, say Gn, okay, in a single particle theory, say using path integral. Okay, so the goal is to calculate this time-ordered product, a correlation function, the vacuum correlation function of this time-ordered product in this theory. Okay, so last time we described how to do this using path integral, and then we derived a beautiful formula. So the formula is given by the following: is that Gn is given by the ratio of two path integrals dxt. So if we call this thing to be x, so the x, and then exponential I s xt, and then the dxt, just the pure path integral. So here I didn't write the upper limit and lower limit. So it should be understood that the boundary condition for both path integral is that the x, so it should be from minus infinity, the time range should be from minus infinity to plus infinity, and then we can choose the value of x at both ends just to be 0. Okay? And yeah. And the slight subtlety is that when you evaluate s, so there should be the epsilon parameter, because in deriving the path integral, we have, say, we need to give the Hamiltonian a slightly, say, epsilon part. So that will also affect your action. So your action will also have a small epsilon dependence. And so at the end of the day, when after you have done this calculation, and then you set epsilon goes to 0. Okay, so the epsilon goes to 0 at the end of, yeah. So when we write epsilon, it's always should be assumed that this is a positive number. Okay, this infinitesimal positive number. Good. Any questions on this? Okay. So now in principle with this formula, then we can now calculate this quantity. Okay, we can calculate this quantity, and we can calculate this endpoint function. So, but in practice, it's actually more convenient rather than to calculate the Gn, because we often need to know such correlation function for different n. Okay, we often need to know such correlation function for different n. So not only, say, sometimes we are interested in n equal to 2, sometimes interested in n equal to 3, 4, etc. Okay, and then there's a nice trick to you can try to calculate then, say, in general, is to use this technique called generating functional, which we started talking about at the end of last lecture. And so the basic idea of the generating functional can be easily understood by consider just this one-dimensional example. Say if you are interested in doing an integral like this, xn, and if you are interested in this integral for different value of integer n, then it's more convenient to consider such an integral, ZA, given by okay. So the reason I put I here is just, yeah, I didn't specify the range of x. And if x is from minus infinity to plus infinity, it's not easy to, yeah, put I here just so that this integral can be defined, okay? Depending on circumstances, you don't have to put I. Say if x is from 0 to infinity, then I can just put, say, minus lambda a, okay, with lambda to be a positive number, and then that's fine, okay? So the benefit of considering this integral is that, oh, no, not the, sorry, I should, x, yeah, xa. Yeah. So the benefit of doing this integral is that if you notice, if you take a derivative with respect to a, and then that will bring down a factor of x, okay? So it's so if you take a derivative with a, you bring down a factor of x, and if you take a derivative twice with a, then you bring down a factor of x squared, and if you do it n times, and then you bring down a factor of x to the power n. So essentially this Zn then can be written as partial n, Za, then partial a, you take derivative n times, and then you set a equal to 0, because in the end we want, in this integral there's no exponential piece, and you set a equal to 0, then you get rid of the exponential piece, then you have factor of xn, okay? So there's still, yeah, so I still need to put in here, okay? So if you know how to compute the Za, and then you only need to take derivatives to do Zn. So taking derivatives is much easier than doing integrals. Okay. So in other words, we can also write it, expand the Za in terms of power series in A, and then the Zn would be the coefficient. Okay. So Zn would be the coefficient for a to the power n. Okay. Yeah. Good. Yeah. So we call this Za the generating function. So now we can use the similar idea to generalize to this case. And now here here just one-dimensional integral. Here we have a functional integral. So now this is the function. So essentially you just generalize this generating function into a generating functional. Okay. And so we can consider the following object. So in order to compute this, then we can consider the analog of this A is we consider object called J. J now will depend on T. Yeah, J is a function. Okay, J is a function because X now become a function. Okay, and so introduce a path integral like this. So from now on, I will not. When I don't write the range, then it's always, you should always keep this in mind. The range is always from minus infinity to plus infinity with the boundary value to be 0. Okay. And then we can just say I have standard x t. Then I can add the analog of this. So remember, again, you think t is just an index, okay? And then you just essentially imagine if you have multiple x, and then you just sum over them, okay? So sum over them, in this case, just corresponding to an integral. And so we just have a piece like this, okay? So this would be the generalization of that equation. And so integration over t just can be imagined as a sum. Imagine if you have multiple x and multiple a, and then you need to sum over them. And then, so this is just a generalization of that. Do you have any questions on this? So now, similarly, now if we take a functional derivative with respect to jt, then we can bring down a factor of xt. Okay, so more explicitly, so let me just remind you that the rule of doing functional derivative. So if you have a function delta jt prime respect to the derivative over jt, and then that just give you a delta function. Okay, they just give you a delta function. Okay. So now let's look at with this rule. Then let's just look at the delta jt on the z. Okay, zj. Okay. So and then yeah. So now since this jt, let's just for convenience, let's just put this to be t prime. Okay. Let's put it to t prime, and then when you take derivative with respect to jt, and then you directly take derivative with this guy, and then when you take a derivative, the delta function will get rid of this integral, and then you just have xt, and then you will just get I dxt exponential is. Okay, and yeah, sorry, we'll get dxt, and then you have a factor of xt. So let me just write dx again to save. You just add dx, and you have xt from taking derivative of jt, and then exponential is plus ijx. Okay, so let me just save some effort. Yeah, you should keep in mind that this in the dt etc. I'm just using a simplified notation. Okay. Good. Any questions on this? So now if I also introduce z0 defined to be z j equal to 0, so this is just the original integral. So z0 is essentially the downstairs, okay? So z0 just the dx exponential is, okay? So when j equal to 0, and then we just have this. So essentially, it's the downstairs here. Okay. So we also let's also introduce this definition. And then we then find, so by comparing the two, then we immediately conclude that the one-point function of x hat t 0 is just given by 1 over I, because there's I there, and 1 over z0, then delta zj, delta jt. And then you set jt equal to 0. Okay, so similar here, if you set a equal to 0, so you take derivative, and then you bring down a factor of xt, and then you set j equal to 0, and then you just have that integral with xt there. And then you get this one-point function. Okay? So now you can just immediately generalize. So this n-point function, gn, then can be written as, you just take one, now you have take n derivatives. Now you have a factor of 1 over I to the power n. Again, you divide by z0 because you always need to divide by this piece. And then you just take the derivative n times. So you take jt1, jtn. So this time variable should match with the time variable in the original definition. Okay. And then after you take the derivative, you set j equal to 0. Okay. So and then this gives you the n-point function. Okay, if you know how to compute this zj, and again you only need to do derivatives, and then it's much simpler. Then you only need to do the part integral once, and then you just doing the derivatives. Any questions on this? Okay. So now if you keep in mind of this, we can also rewrite this expression as the following. Okay, we can also rewrite, alternatively, we can also write zj divided by z0 as following 0 and the time ordered exponential I dt jt xt, okay, 0. Okay? So as I mentioned before, that in that formula, in principle, x can be anything. Okay, x can be anything. So now in this path integral, you can just imagine you separate this term, the sum of the two exponential, you can just write it as a product. Then you have exponential is, and then exponential I, this piece. And then we treat that piece to be x. Okay, and then that gives you this formula. Okay, if you treat that piece to be x, it gives you this formula. Then you ask, what is the meaning when we have a time ordering of this exponential? So the meaning is that, imagine you expand this in power series. Imagine expand in power series of x, and and then you just order each term in the power series. Okay, you can because now each term is a polynomial, you can time order them. Okay, you can time order them. Okay, so now this object, so I can also write this object. So when you expand this object, and then you the first term is just 1, and then the next term just dt jt, then the 1-point function. Okay, and then the nth term, yeah, and yeah, etc. Okay, so you can when you expand it, you can just write from n equal to infinity, 0 to infinity, I to the power n factorial. Now you have n integrals, t1, tn. Then you have times, you have gn, t1, tn, and the jt1, jtn. Okay? So this is the typical nth term is like that. So when you expand this to nth power, you group all the x together, because j is just C number. Integration and the j are C numbers, you can take them out. And then this part is just the x between the zeros, and then you have this factor of j. Okay? Yes?
Where did the n factorial come from?
Oh, just when you expand the exponential, there's always n factorial.
Right, sorry.
Yeah, yeah. Good. Any questions on this? Yes?
Separate out the exponentials, the e to the is and then the I integral.
Yeah.
Isn't like s and like the other term like operator? So like you'd have to have like another contribution from a commutator.
Sorry, again. Say it again.
So like s in that case, like it contains like functions of an operator, and then the other one is also like an operator. So wouldn't that like introduce like commutators?
No, because in the path integral, they're just ordinary functions, right? In the path integral, they're ordinary functions. So in the path integral, they're always just ordinary functions. But then when we rewrite them in terms of the operator form, and then so the left-hand side, so the x, they're just ordinary functions. But in the right-hand side, I'm now writing it in terms of the operator form. And now the ordinary matters. Now the ordinary matters. Yeah. So I'm just using this form. Yeah. So in this formula, the right-hand side is just the ordinary functions, but the left-hand side involving some operator sandwiched between the ground state. Yeah. Other questions? Yes.
So in that formula in the middle, where g is expressed as like the nth function derivative of z,
Yeah.
does it matter what order I take the derivatives?
No, that doesn't matter. Yeah, because again, j is ordinary functions. Yes, yeah, because this is just the path integral. J is just ordinary functions. This is just some functionals of j. You can just take arbitrary derivatives. Also, you notice on the left-hand side, so gn is a function of t1 and tn. So Gn as a function of T1 and Tn is actually completely symmetric. Because under this time ordering, it doesn't matter how you order them. Because they just ordered by time ordering anyway, so it doesn't matter how I write the ordering here. So Gn is a symmetric function of T1 and Tn. So you can see it here. So here, because all the derivative commute, and then this is a symmetric function of T1 and Tn. Yeah. Other questions? Good? Okay. So in the future, we often just computing this object. Okay, we just often computing this object. And then that will tell us, then that will give us the generating function of the correlation functions. Then we can just obtain correlation functions by taking derivatives. Okay. So now let's look at the explicit example to illustrate how this works. So let's just consider a simple example. A harmonic oscillator, okay? So almost always a harmonic oscillator is a good example. Good. So in this case, so again we look at this object, but now S is, so we always now take from minus infinity to plus infinity. You have dt, then you have 1/2. So let's take this to be my Lagrangian, okay? Okay, so let me call this omega 0. Okay, so let's consider such a harmonic oscillator. So I take the m equal to 1. Okay, and I consider this jt. Yeah, we are interested in computing this object. Okay. So also I should mention, in practice, so you're always interested in xt. Say when you calculate endpoint functions, even though the value of t, say suppose you want to calculate gn, okay. So gn, you have n values of t, and so outside that n values of t, you can just take the j to be, yeah. So we can always take j to go to 0 at the plus minus infinity. Okay, yeah. So that helps your integral to converge. Yeah, this is just a side remark. Good. So now, first to compute this object or this object, we need to first understand what is this S epsilon. Okay, we need to understand what is this S epsilon. So remember, so for the harmonic oscillator, the Hamiltonian is p squared divided by 2m plus 1/2 omega 0 square x squared. Okay. And so here is the Lagrangian, and this is the Hamiltonian. They are related by the Legendre transform. So now, in order to do this h, go to h minus I epsilon, and then now this become p squared divided by 2m 1 minus I epsilon, then plus 1/2 omega 0 square x squared 1 minus epsilon. Okay, so you multiply the both terms by 1 minus epsilon. And then to obtain what is the corresponding S for this, you just do another Legendre transform back into the Lagrangian. So then you find that the L epsilon, okay, which you do the corresponding to the Legendre transform of this. Yeah, so this is a trivial exercise which we can do. Then you find that this gets 1/2 x squared 1 plus I epsilon. And then, yeah, so this part essentially does not change. 1/2 omega 0 square x squared 1 minus epsilon. Okay, so that's what you get. Essentially, when you invert it, when you do the Legendre transform to go to p to x, somehow this become from 1 minus I epsilon become 1 plus I epsilon. Yeah, you can easily check yourself. Okay, because you need to do an inversion. And so now let's write this into a more convenient form. Okay, into a more convenient form. So to write it in the more convenient form, we always remember we always treated x as s as some 2x sandwiched by some differential operator. Okay, so we can do integration by part. So we can do integration by part to write it as minus 1/2 x partial t squared plus omega 0 squared, the minus I epsilon omega 0 squared plus I epsilon partial t squared x. Okay, and then plus total derivative. Okay. So the total derivative always vanish because we always we always impose boundary conditions so that t equal to plus minus infinity, and they go to 0. Okay. And so now let's look at this object. So let's look at this object, the epsilon dependence. So omega squared is just a positive number. Multiply epsilon is still a positive number, and epsilon is infinitesimal. So we can just still call it epsilon. So now the partial t squared acting on epsilon. So partial t squared is a lactive definite operator. Okay. Because remember, whenever you do a Fourier transform on x, so partial t, a single factor give you I omega. Then if you have a partial t squared, then give you minus omega squared. Okay, so partial t squared is a lactive definite operator. So that means that this is also a lactive number times epsilon. Okay, and then that means we can just write the whole thing just has 1/2 x partial t squared plus omega 0 squared, then minus epsilon. Okay. X. Good. Is this clear? Yeah, because just any positive thing multiply epsilon still give you epsilon. Okay. Because just a small number, it doesn't matter. Okay, so now we can write this x xt. Now we can write the s epsilon xt. Then in the following form, in the minus 1/2, then we write as dt prime as we wrote before. Then xt k t prime and xt prime, and then ktt prime. Is just given by delta t minus t prime, say partial t prime square minus omega 0 square minus epsilon, or plus, yeah. Okay. So again, we just introduce a lot of t prime, and then I introduce a delta function. And now we have a matrix form. Okay, now again, this action has a matrix structure. So now this S depends on epsilon. Okay, now S depends on epsilon. Good. Okay, good. So now we can evaluate. Now we can ready to evaluate this path integral. Okay, and now we are ready to evaluate the path integral. So let's first look at the z0. So let's first look at z0. Z0 is just the Gaussian the Gaussian integral we already said before. So the z0. So z0 is the Gaussian integral. So I will be schematic. yeah, this x dot k dot x. Okay. So this is a shorthand notation to denote this these two integral. I think it's positive I. Oh yeah, minus I. I have a minus sign here, so it's minus I. Yeah. Good. So and this, as we said before, this is just given by some constant and determinant k. Okay, this just some constant determinant k. Yes. Okay.
Why did you have to go to the Hamiltonian to put that 1 minus I and then
Right. It's because that's our previous rule, right? Because we say, in order to derive this, we use the trick to take the h go to h1 minus epsilon. Yeah. So we want to know how this translates into the behavior in action. Yeah. Other questions? Good. So this is just the same as we discussed before, just given by some constant and determinant k. As we said before, that the C is typically divergent, determinant k so typically divergent, but we will see it doesn't matter. Okay. So how now we will see it doesn't matter. So previously we said this will not matter, but now we will see it explicitly. So now let's look at the ZJ. So ZJ is the same integral. X dot k dot x. But now with this additional term, so let me just write again in the simplified notation as j dot x. So you view the integration as a huge sum of vector product. Okay. So if this is a finite dimensional integral, you say I know how to do this. Okay, we know how to do this because this is just the Gaussian with a linear piece. Okay, with a linear piece. So we can just write down the answer. So let's just the rule is that you just treat it as a finite dimensional integral. Write the answer for the finite dimensional integral, and then you translate the language in terms of this functional case. Okay, so we can write it. So again, this would be C divided by delta k. Yeah. So let me just remind you. Maybe let me just do a little bit slower. So let me just remind you the standard story for such a Gaussian integral. So if you have the x1, the xn, exponential minus 1/2 xi aij xj plus ji xi. So if you have an integral like this, we know how to compute this integral. You can just include xi into here by completing the square, and then what you get is the following. After you complete the square, you just get the original Gaussian integral. And so what you get is you get the 2 pi d over 2, your previous case delta a. And then the result you get from the completed integral is ji a minus 1 ij jj. Okay, so when you complete the square, you get the additional term, that's what you get. And this is come from doing the Gaussian integral. Okay? So now we just have an infinite dimensional version of this integral. And we can just write down the result immediately. Okay? We can just write down the result immediately. So we just copy that thing. So we have C. So this C will be exactly the same as that C. Okay? Because this just comes from doing the Gaussian integral as if J is not there. So we have the same C, we have the same delta K. Then according to the rule there, up to the I, which is you have to put in, then we get 1/2 I. Then we should have J, K minus 1, J. Okay? So this is essentially that. Okay, you take the inverse of A. So here we get that. And this, if we translate back into this kind of function language, so this just gives you C delta K exponential I divided by 2. Then you have dt prime. Then you have jt k minus 1 t again t prime. So k minus 1 should be understood as the inverse of this k and jt prime. Okay. So the k minus 1 is defined as follows. So the k is, so it just again is the function generalization of the a matrix case. So you just have t prime, k, t prime, and k minus 1, t prime, t double prime should be equal to delta t minus t double prime. Okay, so that's how you define the k minus 1. Again, this is like a matrix product. Just now you treat the t prime, t prime, you sum over that. And then, so this is just like you have k mn, k minus n, and k equal to delta mk. Okay, you just translate the n into the integral, and the t is corresponding to m, and the t double prime corresponding to k, and the delta function corresponding to that. Okay, so that's how we define the k minus 1. And so this is the result for ZJ. Okay. So now the physical object is this object is the ZJ divided by Z0. Because to get the expectation value, we always need to divide by Z0. So now if we take the ratio, so now I can erase this. So if we take the ratio, Zj divided by Z0, we find all these factors cancelled. Okay, so this factor cancelled with that factor, so it doesn't matter. So we just get exponential. So let me again using this shorthand notation, I over 2 j k minus 1 j. Okay, so this is the physical quantity. Okay. And when we expand this in powers of j, then we get the correlation. Then the coefficient of j give you correlation functions, or we can just take derivatives. Yes.
Yeah. So last time I thought we said like the c and the determinant of k could be infinite. So is it okay to divide infinity by infinity and just say it's 1 in this case?
No, it's not 1 because they are actually as you do in your p set. Say if you have a free particle, that ratio is actually you can calculate to be a finite number. Even though their ratio is actually both are infinite, but the ratio is actually a finite number. Yeah. Same thing with the harmonic oscillator. Yeah, but the key thing is that we actually don't need to worry about them. They just cancel. Other questions? Okay. So now this is our final result, okay, for the harmonic oscillator. And except we still have to invert this k. Okay, we still have to invert this k. But in fact, okay, but before we do that, we first we can see what is whether there's any physical interpretation for this k minus 1. Okay, for k minus 1. So let's just consider the following situation. So let's consider a 2-point function. So first, from here you can immediately see the 1-point function is given by what? The vacuum 1-point function of x So can you see what is the vacuum one-point function for x without doing calculation? Yes, 0. So the reason it's 0 is that because if you get one-point function, you take one derivative with j. So when you take one derivative with j, because here it's j squared, you will bring down a factor of j. Then when you set j equal to 0, and then that will be 0. Okay, so the one-point function automatically is 0. Okay, and that's consistent with our expectation. In the harmonic oscillator, the one-point function of x is always 0. Okay, because x involves a or a dagger. When you sandwich between two zeros, it's just 0. But now, so the non-vanishing one is the two-point function. So now let's consider the two-point function. So two-point function by definition should be the Feynman function. Okay, because this is the time-ordered product. Okay. So the two-point function by definition is the Feynman function. It's the G2. Okay. And so this is given by just this thing expand, yeah, just 1 over z0 I square. You take zj, two derivatives. Okay. Delta jt, delta jt prime, and then you take j equal to 0. Okay. So the two-point function is the Feynman propagator. So here we can just see what we get from here. So when you take two derivatives on this, you take two derivatives on j again. So the first derivative on j, you bring down a factor of k times j. And your second derivative, we can do two things. You can act on the exponential again, and then you can act on the j factor which you bring down the first time. But you have to act on the factor of j you bring the first time because you have only free j left, and when you set j equal to 0, that will be equal to 0. Okay, so both derivatives should act on this j which come together. Okay, so here then you get minus I, essentially k minus 1 t and t prime. Okay, just take these two derivatives, then you get k minus 1. Okay? So now we learned something nice. Is that this k minus 1 is actually the Feynman propagator we discussed before, the Feynman function we discussed before. Yeah, the harmonic oscillator version of the Feynman function. Okay, so previously we defined for the field theory. So this is the harmonic oscillator version of the Feynman function. So we find that k minus 1 tt prime is just equal to actually I gf tt prime. Okay. So you find that this is just given by gf. Okay. So then we learn that the zj divided by z0 is just equal to exponential now minus 1/2 j gf j. Okay? So now it's just gf. It's just everything determined by this gf. Okay. So now we have a consistency check. Okay, now we have a consistency check. Because previously we have discussed that the GF should satisfy certain differential equation. Okay, and here we have a differential equation for k. So k minus 1 also satisfies a differential equation. It just satisfies this equation. Okay, and so now if you plug in there and into here, okay, if by definition, so from this equation, so let me call this equation star. star star, and this equation star. So from equation star and star star, and we find that k minus 1 should satisfy the following equation. Okay, that partial t square minus omega 0 square plus omega 0 minus epsilon gf, yeah, k minus 1 should be equal to the delta t minus t prime. Okay, so let me just make sure I get the sign correct. Yeah. So, yeah, I think this is right. Okay, and now if you plug in this expression, and then you find that this equation is actually exactly our definition of the Feynman propagator before. Okay, here we don't have spatial derivatives, but if you look at it, in particular this epsilon, it's precisely epsilon previously we need to use to define the Feynman propagator. And now we find that the epsilon prescription which we previously used as a trick to define the Feynman propagator is actually recovered by this procedure. Recovered by that procedure of h goes to 1 minus epsilon. Okay. Okay, just everything is consistent. Just now we precisely recover that procedure. Okay. Any questions on this? Yes.
So I guess in that expression right there,
Yeah.
If like j is a function, do you just integrate over like t and t prime? The exponential negative half j dot g.
Oh, you mean this expansion?
Yeah.
Yeah. So if I write it explicitly, you just have, let me write it explicitly since this is a very important equation. Yeah, so this is just dt prime, jt, gf, t prime, and jt prime. Yeah. No, good. Right, so this is all consistent. Okay, so this epsilon prescription which we did here automatically recovers epsilon prescription in the definition of the Feynman function we defined before. So it's very nice. Okay. And in particular, so in momentum space, if you Fourier you find the momentum space gf omega. If you go to the momentum space, and then you find just equal to I omega square minus omega 0 square plus I epsilon. Okay, so you see this is actually the so if you compare with our previous expression for the Feynman function, when you set k squared to 0 and replace the omega 0 square by m square, then that's exactly the one we derived before. Okay, derived before. Good. So now we can try to find endpoint functions. So now we can work out all endpoint functions. So now you can immediately conclude, okay, you can immediately conclude from the way we do the one-point function that the all endpoint functions, so general n, for general odd n, Gn is always 0. Okay, Gn is always 0. So the reason is the following. When we carry out this procedure to take the derivatives, so because the j is always paired in this exponential, so when you take one derivative, you will bring down another j. So because in the end we set j equal to 0, so you have to get rid of all this kind of j which you bring down from the exponential. And then that means n has to be even. So if n is odd, there's always one j left. And when you set j equal to 0, and then will be 0. Okay. So this is also consistent with your experience from a harmonic oscillator. Because in the harmonic oscillator, if you have odd number of x, then you have odd number of a and a dagger. If you have odd number of a and a dagger together, there's no way when they sandwich between 0 and they can annihilate each other, and you will so you will always get 0. And so here we get it So now for the even n, there's also a simple answer. Okay, if I have an n-point function, so let me just write down Gn, say equal to 0, t say x hat t1, tn. So for even n, then you see that, again, because in order for this not to be 0, then all the x has to be paired. Okay, then all the x has to be paired. So in this case, we just sum. So in this case, the answer is just sum over all possible contractions between xti's. Okay. So by contraction, we mean, so if I have xti, xtj, we say there's a contraction between them, and so that's just defined to be gf xi xj. Okay. Oh no, ti tj. So you just pair all of them. So each pair is a contraction. You just sum over all possible contractions, pair all of them, and each pairing give you a Feynman function. Okay, so each pairing give you a Feynman function. And so this is actually in the early days of quantum field theory, when you don't have a path integral. To show this is actually non-trivial, because imagine if you do this time-ordered product. There are many pieces, right? Because if you have an n-point function, then you have to write down all possible orderings between them. But in the end, it's a very simple result. Okay, just sum of all possible contractions, and each pair is the time ordered. Okay, and so this early days without path integral is actually a highly non-trivial result. And so this was first proved by Wick. So this is called the Wick theorem. Okay, but now we see it's actually, if you know the path integral, then it's a trivial consequence of that the path integral is actually quadratic in J. Okay, just quadratic in J. So yeah, so give you example. So let's look at 4-point functions. So if you look at 4-point functions, so I don't even have to write that thing down. Let's just draw 4 dots below to the 4 points. And then I just sum over all pairing between them. And each pairing will give me a Feynman propagator. So 1, I can pair 1 and 2, or 3 and 4. And I can also pair 1 and 3, and 2 and 4. And I can also pair 1 with 4, and 2 with 3. Okay, or 2, so 2 is here. So 2 with 3. I can also do that pairing. And so if I write it in terms of the expressions, then I have GF T1, 2. Let me just T1, T2, GF T3, T4, plus GF T1, T3, GF T2, T4, then plus the GF T1, T4, plus times GF T2, T3. Okay? So you just sum over all such pairings. Okay, and each pairing give you a GF. Okay, yes?
So I thought because of the time ordering, you can't like choose your pairing at the point. There's only one way to pair.
What do you
Why is
mean?
it okay to do the different pairings even though things are time ordered?
What do you mean you cannot do the pairing?
Like the X's are time ordered.
Yeah, yeah.
So wouldn't you have to pair them in that order?
No, so that's the key. Just somehow this is the consequence of the theorem. If you want to just write down the orderings, then it's actually rather complicated. Yeah. But somehow the magic is that once you say write everything explicitly, you do all the you do all everything. In the end, you can group everything just in terms of product of the Feynman functions. Yeah. Yeah. Yes.
So for the harmonic oscillator, we know that at a given point in time,
Yeah.
Position is Gaussian, and so that would mean that like the endpoint function for all the t's equal to each other should be non-zero only for n equal to 1 or 2, but not for n greater, right? Because like only the first 2 moments of a Gaussian are non-zero. But like that seems inconsistent with this prescription over here.
Sorry. Why you're saying that?
Like at a given time,
No, but all this time are different.
right? But if I were to take the times to be equal,
Okay. Yeah.
then, so like, for example, the variance of the particle position would be your 2-point function evaluated at t.
Yeah.
T.
Yeah. This is just the x to the power n.
Right.
Yeah. X to the power n is non-zero for even power.
Yes, but then in this formula that would be gf of t
Yeah.
comma t,
Yeah.
which is non-zero.
Yeah.
But
Yeah, but GF0 is non-zero.
right, but then what I'm saying is the 4-point function then would also give you something non-zero.
Yeah, it is non-zero.
But,
Yeah, it's very
but
consistent.
the 4th moment of the Gaussian is 0.
No. The first moment of Gaussian certainly is non-zero. Yeah, x4. Yeah, Gaussian you have x4. That's certainly non-zero.
The mean is 0, so it's like all cumulants higher than 2 for a Gaussian.
No. For the Gaussian, just all higher equivalent can be expressed in terms of the sigma, in terms of the 2 points. Yeah, here is just exactly what you show here. Yeah, just everything can be expressed in terms of the 2-point moment. Yeah. So if you set all the t to be 0, so this is GF is the same. So this is GF. Essentially, the only dependent difference between them. So this is GF. Yeah, essentially just add them together, just 3 GF squared. And yeah, just do this exercise yourself, and you will see it's the same. Yeah. Good. So now with this preparation in quantum mechanics, now we can immediately just move in field theory. Okay. So now we can immediately move to field theory. So now we can say time-ordered functions in field theory. So before we do that, any other questions? Okay, good. So again, to go to field theory, now the only thing we need is just copy notations. Okay, you just need to change the notations. Just remember how you, just replace the appropriate dynamical variable in quantum mechanics by the appropriate dynamical variables in field theory, and then that's it. Okay. So let's write down. So now we have considered in field theory. Suppose we consider this endpoint function, and now x and xn now denote the space-time point. Now, okay. So let me call the. Previously we called the vacuum for the field theory to be omega in the interacting theory. So now you consider this quantity, phi x1 and the phi xn. Let's look at this endpoint function between the vacuum. Okay. So now again, if we call this thing to be x, so now we can immediately write down the answer in field theory. Just the d phi. Now you just replace dx by d phi. Then you just have this x, capital X, and then you have now as phi, then divided by d phi without as phi. Okay? And now the boundary condition is that the phi, when you do this path integral, again t goes from infinity to minus infinity to infinity, and now tx should go to 0 for both t plus minus infinity. Okay, so that's the analog of a previous thing for x equal to 0. Okay, and because here, remember the x here is just the labels, and so for each variable we require it's go to 0 at t plus minus infinity equal to 0. And also normally in field theory we assume, in order to for the integral to have well-defined behavior, etc., we often just assume also go to 0 when in the spatial infinity. Okay. Yeah, this is just for often for convenience. Okay. And physically, this also means that at the infinity far away, and we assume that the field are not excited. Yeah, we are interested only in the physical excitations in finite region. Anyway, so this is the condition we impose when doing the path integral in the field theory case. Okay. So now again, you can introduce a generating functional. You can just copy notation, copy the previous formula, and by changing notation. So now the generating functional ZJ is defined to be d phi exponential is phi, and then now you just add. Now you integrate over all space-time point and phi x. Again, we introduce a j, but now you integrate over all space-time points. Okay. And then similarly, the zj divided by z0. So this we call the z0. Z0 again is just the integral without x, any x. Okay. So divided by z0 is equal to now the omega and time ordered product of the exponential I. Okay. So again, just given by that, and again, this time ordered product, time ordered exponential should be understood as you expanded this in power series. When you expand it in power series, then you have powers of phi. Then you just order those phi's in terms of time ordering. And then again, the integration and j can be pulled outside this expectation value. Okay? Good. And z0 is just the same as z j equal to 0. Okay, so without any j. Okay. So this is again just immediately give you a general prescription for calculating endpoint function in any theory, in any scalar theory. So here I don't even have to specify the precise form of the action. Okay, it just carry through. Okay, carry through. This also applies to interacting theory. So this formula also applies to interacting theory, and yeah, it's a very general. Very general. So this is the power, say, of the this path integral formalism. Okay, so once you understand in the quantum mechanics case, go to quantum field theory, just automatic. Okay. Good. So now let's look at how to treat how to do this thing, calculate this thing in field theory. So first let's just look at the free field theory. And then before we look at the interacting case, let's just look at the free field theory. So free field theory is almost identical, again, almost identical to the harmonic oscillator case. And because harmonic oscillator is also, because the free theory will be also a quadratic Gaussian integral, so everything will be very similar to the harmonic oscillator case. We just need to, again, replace some notations. So now let's consider the free field case. Consider this minus 1/2 partial mu phi minus 1/2 m squared phi squared without any nonlinear, without any cubic or higher power term. And again, the S can be written. So S in this case, so here 0 means the free theory because later we will do interacting theory. Okay. So S in this case, again, you can write it as you can integration by part. You can write it as d4x prime, then phi x k x prime, and then phi x prime. Okay. And now the k is given by, say, square plus m square minus epsilon. Again, this epsilon comes from that thing. It just, yeah, if you walk through, it just, yeah, it just minus epsilon, and then delta 4x minus x prime. Okay. And yeah. Good. So again, we can just the shorthand notation, write it as this has minus 1/2 phi dot k dot phi. Just now, the only difference is that you change it from integration over dt, the integration over the full space-time. Okay. Yeah, everything else is the same. And now this zj, just given by d phi exponential, again, just given by a Gaussian integral. So let me see whether I can squeeze in by a Gaussian integral phi dot k dot phi, then plus ij dot phi. Okay, so we can again write this in the simplified notation as ij dot phi. Okay. So again, you just and then you find this. You get some other c. Again, you get determinant k, and then you get exponential I over 2 j k1 j. Okay, so everything is exactly the same. And then this is the same as z0, this part. And then again they cancel. Again they cancel. Okay. So again we find so in this case again we find that k minus 1 x prime equal to I GF x prime. Okay, so this epsilon prescription, so it's precisely, yeah, if you check the definition, so this epsilon prescription m squared goes to m squared minus epsilon is also precisely what we did before for the Feynman function. Okay. So now the final answer, the ZJ divided by Z0, yeah, almost don't want to copy it. It's just exactly the same as this. You just replace the dt integral by d4x integral, okay? And d4x integral. So yeah, let me just write it. Exponential minus 1/2, then j, gf, j. Okay? Any questions on this? And again, if you calculate endpoint function, then you just get identical structure as here. Okay, just get identical structure here. The only difference is that you replace GF T1, T2 by X1, X2, X3, X4, etc. Everything is just identical. Okay, so to save time, I will not copy them again. So do you have, yeah?
So in this preview theory, do we have the condition that phi goes to 0, but t goes to infinity?
Sorry?
In this preview theory, do we have the condition that phi goes
Yeah.
to 0?
Yeah. So that ensures when you do integration by part, everything is 0.
But we have the solution for phi.
Sorry?
Like we know the solution for phi in terms of x and t, right? And it's like width, plane width.
No, this is the boundary condition in your path integral. Yeah, this is the boundary condition in your path integral. We're not talking about this. Yeah, so this is, phi just the, here I didn't write down any explicit solution for phi. Sorry, what plane wave we are talking about?
Oh, I was talking about the solution for phi in the preview theories that we did like a few lectures ago.
Right.
So that doesn't answer here, right?
Yeah, no, that will also go to 0. No, that's an operator equation, right? That's an operator. Here is just the field in your path integral. So here you just integrate over all possible. When we write that, that's an operator equation with a and a dagger there. So here is just the ordinary function of space-time, which we impose the boundary condition in the path integral. Yeah. And similarly, in here, there's a Wick theorem. Okay, just everything just goes through. Okay, everything just goes through. Good. Any other questions? Okay, so for the last few minutes, then we can venture a little bit into the interacting case. Was there any question? Okay. Okay, so now we can venture into interactions. Okay, so now we have our master formula, and now we can treat what happens in the interaction case. Okay. So now we can go to interacting theory. So in the interacting theory, let's just consider, say, the case which L equal to L0. Then you plus some polynomial, okay, for example, the simplest case is just lambda we discussed before to the phi 4, okay, so plus some higher power term. So for simplicity, I will just, but what we will do will not depend on details form. Let me just write Li. Imagine there are some interacting terms, okay? So in this particular case, the Li is equal to that, but we can consider more general case. Just you have some extra, something depend on phi, okay? And similarly, your Hamiltonian will also be the free series Hamiltonian plus an interacting one, okay? And the interacting one, so let's for simplicity that this Li, as in this case, only depend on phi, does not depend on the, say, the time derivative of phi, okay? So if it does not depend on time derivative of phi, and then essentially Li, Hi is essentially just minus this 3x Li. Okay, when you do the Legendre transform to go from, say, L to H, that don't change this term, okay, if it does not contain time derivative. So, and then there's a very simple relation between this interacting term in the Lagrangian and also in the Hamiltonian, okay? And this is a free series Hamiltonian. And now we will write our total action in terms of the free series part and the interacting part. And the interacting part is just given by d4 xli. Okay, it's also the same as minus dt hi. Okay. Good. So just to set it up. And now we want to calculate, again, we want to calculate this endpoint function. Did I erase it? Again, we want to calculate this endpoint function. Yeah, so this is the object we are interested in. Okay. And again, we can just consider generating functional. Okay. And we can consider generating functional. Before actually we do that, let's just consider. Let's just consider this endpoint function. Yeah, we actually have 1 minute. We cannot do really much. Let me just tell you the basic idea, and then we will elaborate next time. So now let's imagine we want to compute this object. Again, we just use that formula. This Gn is equal to d phi x exponential is divided by d phi exponential is. Okay? So now what I will do is I will, now my is, so the idea is the following. Now these path integrals now are not doable, because once you have these non-polynomial terms, or non-quadratic terms, we don't know how to do the integral. Okay, we don't know how to do this integral even for one-dimensional integral. Okay, so not to mention the path integral. Okay, we also don't know how to do such integral for a harmonic oscillator. Same thing. We don't know how to do it for field theory. So as we said before, even though we don't know how to do this integral, we can treat this perturbatively. So we treat this as the main term, and then we treat lambda small, then we try to expand in power series of lambda. Okay? And now we can write the path integral as the following. d phi x, then we add s0, then isi, and then divided by d phi exponential is0 plus isi. And now what we are going to do is we just expand this term in power series. when we expand this in power series, and then essentially we are reducing it to the path integral of the free series. Okay? So essentially the upstairs and downstairs can be imagined as we are doing the free series. Now this is a free series vacuum. Okay, we can just view this as in the integrand of expansion I0. Okay, so the upstairs just become. So this just become the T x expansion ISI now in the free series, and then downstairs also becomes 0 T expansion ISI in the free series. Okay. And now we can just evaluate in the free series such kind of correlation functions, and we evaluate them by expanding the SI in power series. Okay, and then just so everything become just doing some Taylor series expansion in the inside of the integral. Okay, and then become very simple. Okay, you don't need any fancy stuff. First year calculus you can do. Okay, first year calculus you can do. Okay, so when you expand those stuff, still you get something very complicated, and then you can use diagrammatic rules to simplify them, and that's called Feynman diagrams. And now we can, next time we will talk about Feynman diagrams to simplify such kind of expansion in power series. Okay.